Hey guys, so what we're going to be taking a look at in this video is how to do integration using long division. What you saw in the previous video at the very beginning, and if you have your notes handy you can go back and look at it, was when to use long division when U substitution isn't an option. So what we would do with long division is we're looking for a rational expression where typically the degree of the numerator will be greater than the degree of the denominator, or they could actually be the same. It could be a balanced rational function. And what we'll do is we will do the actual division to simplify the expression into having a, instead of it being a rational expression, it'll look much more like a typical polynomial. And then we will then take the antiderivative of it so we can finally integrate it. Now, one of the things that you do need to be aware of is that you may use long or you may use synthetic division. And depending on what your divisor is, meaning your denominator, you may want to use synthetic division more than long division. Synthetic division can only be done when your divisor is a first degree polynomial. So make sure that if you're not familiar with long or synthetic division or polynomial division in general, you may want to go back to your pre-cal material and look that back up and see how you did it then. Or you can just kind of follow along, and hopefully the examples that we'll look at will be enough of a refresher for you. So taking a look at this example that we have here, the divisor, the denominator, is a first degree polynomial. So straight away it tells me that I can use synthetic division for this. And we do want to use division to simplify the rational expression because U substitution isn't going to be helpful. So going back to what we did for synthetic division, we take the denominator and we set it equal to 0. So if I take the denominator and set it equal to 0, in this case I'm going to get a -4. Now every textbook teacher kind of does synthetic division slightly differently. I kind of use just an upside down division symbol where I have enough space for 2 rows. And we take the coefficients of the dividend, meaning what we're actually doing the division into. And so I have a 3, an 8, I have a -10, and I have a +15. And the process is we just bring down the first number and we multiply it by the divisor, the -4s. So that will give me a -12 that I put underneath the 8 or whatever. We put it in the bottom row of the next column. We add those numbers together and that'll give me a -4. And then I multiply again, which will give me a +16, and add those numbers, which will give me a +6. Multiply again, which will give me a -24. And then finally add those, and I get a -9. Well, this number right here, the last number, that is your remainder. And that's essentially where we stop now. So because I divided a third degree polynomial by a first degree polynomial, we really, we are left with a second degree polynomial for our quotient, for our solution. So this becomes 3x squared minus 4x plus 6. And the way that we express the remainder is I'm going to say plus whatever the remainder is over the divisor of x plus 4 in this case. And this becomes, and why isn't my pen? There we go. This becomes our new term that we're going to integrate. And because we have a polynomial expression for a majority of it, it's relatively easy to do. So when I take the antiderivative of everything that I have here, I wind up with x cubed minus 2x squared plus 6x. And the antiderivative of the ratio will give me a -9 times the natural log of x plus 4. And then we add our constant because we have a indefinite integral that we're doing. And that is your solution. That is your integration with division. And I want to say division because there's nothing saying that you have to use long division. If synthetic division works, great, use it. So if you want to, go ahead and pause the video here and see if you can work out this example using the division process, either long division or synthetic division, and see what you end up getting. And presuming that you've done that, we're going to go ahead and divide the function here, because this is a rational function that's balanced. The degree of the numerator and the denominator are the same. We can do the division process for integration because u substitution isn't going to be a viable option for this example. So setting the denominator equal to 0, I'm going to get a positive 1. Looking at the numbers of the dividend, the numerator, I have a 1 and a negative 5. So multiplying through, bring down the 1, multiplying, I get a 1 here, negative 4. So a first degree divided by a first degree is just going to give you a constant, a number that's left over. So this is just going to be 1 minus 4 over 2x minus 2 in this case, over the, and that didn't come out very nicely, 2x minus 2, whatever the divisor happens to be. And this becomes the new expression that we're going to take the integration of. So the antiderivative of the constant will give me 1x. The antiderivative of the ratio will give me a negative 4 times the natural log of 2x minus 2 and plus a constant because we're doing an indefinite integration. So moving on to our third example here. Again, feel free to go ahead and pause the video and try to work it out ahead of time to see what you get and then compare it with what I do. So again, synthetic division is a perfect choice here because the divisor is a first degree. So I'm going to set it equal to 0 and I get a 1 for its solution. Now whenever I do long or synthetic division, we do have to make sure that all of the exponent values are missing. So x squared, I'm sorry, I said that backwards. We need to make sure if any exponent values are missing, and we have to incorporate those if they are. So x squared and, not plus, and x to the 0 power, where our constant would be, both of those are missing. So where those are missing, we do have to incorporate a 0. And this is true for long or synthetic division. Anytime an exponent value is missing, you have to put a 0 in as a placeholder for it. So looking at that, I have a 1x cubed, a 0x squared, a 1x, and a 0 for my constant term, x to the 0 power. So dividing now, bring down the 1, multiply, add, and multiply. This is what we get. So this is my remainder here. So dividing a third degree by a first degree gives me a 1x squared plus 1x plus 2, and then the remainder will be 2 over x minus 1. And this becomes the new expression that we're going to integrate. So taking the antiderivative of the expression in this case will give me 1/3 x cubed plus 1/2 x squared plus 2x plus 2 times the natural log x minus 1 plus c. And there's our expression for our integrated solution. Now this is going to be the last one that we do specific for just basic division. And this one we have to do long division because the divisor, the denominator, is not first degree. It is a second degree. So we have to do long division. So we kind of do this the same way that we did long division back in like 4th grade or whenever you did it. So we have x squared plus 2x minus 3, and we're going to divide it into, and again, there's no missing exponent terms, but you do need to check for it. So we have the 2x cubed plus 1x squared minus 11x plus 20. Okay. So the way that we do long division is we start by taking a look at the leading terms. So I'm going to compare the leading terms to each other as a ratio. Oops. And in this case, I would say 2x cubed over 1x squared, and I would just simplify that ratio, which would, in this case, simplify to be 2x. So I'll take that 2x and I'll put it over the x column of my problem, or of my dividend, really. And now we multiply. So let's go ahead and get rid of these lines here so they don't confuse anybody. Okay. And we multiply just like we would normally do in long division. So 2x times x squared gives me 2x cubed. And then we get multiply the next term, and I get a positive 4x squared. And the last one will give me a negative 6x. Now I am subtracting an expression, not just an individual number, so I put that expression in parentheses because the negative sign needs to be applied to everything. So subtracting now, 2 minus 2 gives me 0. 1x squared minus 4x gives me negative 5x squared. And then negative 11x minus negative, oops, I did that backwards, didn't I? I'm not paying attention. Somebody at home is yelling, hey, you made a mistake. So let's go ahead and fix it here. 1 minus a 4 is a negative 3, not a negative 5. And so negative 11 minus negative 6, that one will give me a negative 5, and this is squared x. And then we bring down the 20. Well, at this point now, we kind of have a new leading term that we continue doing our division with. So I have a leading term here, and this leading term doesn't change. So if I say negative 3x squared over positive x squared, that simplifies to be a negative 3. And that goes negative 3 here over the constants column of the dividend. And we repeat the process. We're going to multiply the number from our quotient to the divisor. So we get a negative 3x squared when we multiply those terms together. Negative 3 and a positive 2 give me a negative 6x. And a negative 3 and a negative 3 give me a positive 9. I put it in parentheses to show that I'm subtracting the entire expression and see what we wind up getting. So negative 3 minus negative 3, that gives me a 0. Negative 3 minus a negative 6 gives me a positive 1x. And 20 minus 9 gives me a positive 11. So this is my remainder, and this is my quotient. So my new expression that, and let's go back to my original color for the problem. My new expression for my integration will be the 2x minus 3 plus the remainder of x plus 11 over x squared plus 2x minus 3 dx. Now, some of you may be looking at that remainder and saying, well, Mr. Piercy, how are we going to simplify that remainder? What are we going to do? Because, you know, I can't look at it and say that I'm going to, if I can't use U substitution here. But I would say, aha, you are correct. But we do have a proper rational function that we can use integration by parts with. And be like, oh, hey, I knew that. And so that's what we're going to do to simplify that remainder expression. So let's go ahead and take a look at how we're going to break that up by doing partial fraction integration. So we have the 2x minus 3, and we'll go ahead and just put a dx here. And then we're going to break this up into, you know, our a over, and we're going to factor the denominator. And the factors of the denominator in this case will be an x plus a 3 and an x minus a 1. So I'll put the x plus 3 here. And dx plus this will be b over the second factor, which would be x minus a 1 dx. And we need to figure out what are the values of a and b. And hopefully you can work this out on your own based on what we did for the partial fraction video that preceded this one. So if I want to find a, I'm going to take the denominator of a and set it equal to 0 and solve for x, which will in this case give me a -3. And that -3 is going to be substituted into the, anywhere I have an x from the numerator and the second fraction's denominator. So that'll be -3 plus 11 over, and we look at the second denominator, so -3 minus 1. So that'll be, what, -8 over a -4, which would be a -2. So that's what goes here for A. And now let's do B. So for B, we'll set its denominator equal to 0, which would be x is equal to a +1 in this case. So in the numerator, I'm going to substitute 1 plus 11 for x. And the denominator, we look at the denominator underneath a now, so that'll be 1 plus 3. So 12 over 4 simplifies to be a +3, so that's what goes here for B. And go back to my blue color. So we have the integration of the 2x minus 3 expression. We have the integration of -2 over x plus 3 dx. And we have the integration of +3 over x minus 1 dx. And now we can take the derivative or the antiderivative of each piece and see what we wind up getting. So the 2x minus 3, when I take the antiderivative there, I'm going to wind up with x squared minus 3x. The antiderivative of the fraction will give me a -2 times the natural log of x plus 3. And the second fraction will be the similar expression here, will give me 3 times the natural log of the x minus 1 denominator. And because we're doing an indefinite integral, we add a c at the end. And this is where we're going to stop our division portion of our video. There are 2 more examples for this set of notes that we're going to take a look at, but we will have to use U substitution in order to try and work them out. So we're going to go ahead and stop here, and there will be one more video to follow. But until then, guys, take care, be good, talk to you later.